Gracias. Hola, soy Matt Glanville. No hablo español. Gracias por su comprensión. Carga dinámica de viento de fachadas modernas. Dinámica de la fachada a las cargas de viento. Túnel del viento de capa límite. We have a photograph of our boundary layer wind tunnel in Sydney. We have a subject tower in the centre of the turntable. And we have all the buildings within a 500-metre radius modelled. We can rotate that turntable to simulate different wind directions. Now we call it a boundary layer wind tunnel because it generates a boundary layer. The boundary layer is generated by a combination of these roughness blocks, the spires at the end, and a tripboard. And what that does, it generates a generic turbulent boundary layer at the end of the fetch. We call this length the fetch. The wind is flowing towards us. The profile varies in velocity and turbulence intensity according to codified profiles. And importantly, there's a spectrum of turbulence that we simulate in the wind tunnel. That generic profile gets modified across the turntable of the actual surrounds, so that by the time the wind hits the subject building, we're simulating the actual wind forces it's going to see in real life, but at scale. Now, the primary output from the wind tunnel is a forcing spectrum. If you like, it's a recipe of the turbulence. It's a function of the frequency in the horizontal axis and then the energy in the turbulence in the vertical axis. And in the wind, most of the energy has periods around sort of 1, 10 to 10, up to minutes in duration. You know from your common experience when a windstorm comes through, every 10 seconds, 15 seconds or so, you'll feel a gust come. And this is defined by this turbulence spectrum. Now, this is what we simulate in the wind tunnel. Now, structural engineers, when they're designing, say, a high-rise tower, they have an FE modelling program. And one of the outputs is dynamic properties. And the dynamic properties include natural frequencies, mode shapes, and includes a mass distribution. Now, from that information, we can calculate a mechanical admittance function, or in other words, a dynamic amplification factor. What it does is it allows for us to account for the amplification of response of a tower at its natural frequency. And obviously, this is an exaggeration of the Empire State Building, but at a reduced amplitude, it does vibrate in this shape and with a natural frequency. And it'll have a heightened response to the natural frequency proportional to the damping of the structure. A little bit of sort of mathematics and graphics here, but basically what we're doing is combining the force spectrum from the wind tunnel, the dynamic amplification factor that's essentially provided by the engineers on the project. We combine the two and we get a dynamic response spectrum. And traditionally, a lot of structures, such as high-rise towers, have first mode natural frequencies less than 1 hertz, where there's a lot of energy in that wind turbulence to excite the structure. So whilst we have a large background component, that's low frequency drifting of the tower backwards and forwards, there can be very significant resonant response, and there can be significant resonant response in the serviceability range of wind speeds. And this can impart motion on the tower, which is an acceleration that can be perceived by humans. And there can be perception of motion problems in high-rise towers. And a lot of the work we do is with high-rise to anticipate this and design out any potential motion problems. Now, for most facades, conventional facades, where we're talking floor-to-ceiling spans, the natural frequencies are much greater than 1 hertz typically. So in terms of our dynamic amplification factor, it's pushed across this way where there's less energy in the turbulence spectrum. So conventionally, for most facades, the resonant component dynamic response is small, and we can treat the load as quasi-static. We have a flow visualization. This is a wind tunnel model. Flows moving from right to left. We have smoke so you can see the flow patterns. This is a time trace of the same time history of pressure at this location. And you can see the highest pressures come from a negative. We get this flow separation, which you get a negative pressure enveloping this point of discontinuity, or downstream of the point of discontinuity. And we can see sometimes we get these like recirculations or local accelerations adjacent to the facade, which give rise to these intermittent peaks, which can't really be predicted without the benefit of wind tunnel testing. Even sophisticated numerical programs such as computational fluid dynamics have problems reproducing these peak loads. But in the wind tunnel, we can model. The apparatus is a 1 in 400 scale model, typically with holes over the facade and tubes which run transducers under the tunnel. And the output from the study is what we call a zone diagram. Now, the primary purpose of this study is to identify the hotspots. And that's a zone, usually it's a localized zone of pressure, which can actually be above the magnitude of what the local wind codes would predict. So our primary focus is to make sure the structure is safe by identifying these hotspots. And it's a quasi-static load where we're not including resonant components because of the high natural frequency typically on curtain wall facades. But what we do find is by doing this test, empirical test, that a lot of the facade area is below code. And it does become a value engineering exercise. Some independent work that was done by Meinhardt Facade Technology on a particular project in Bansar in Kuala Lumpur, was the project shown in the slide earlier in the wind tunnel. There's over $1 million savings in terms of aluminium and glass. And for a cost of a small test, we're getting a 60-fold payback on that investment. Diminuendo aeroacústica de la fachada. Now, with modern facades, we're adding ancillaries to the facade. We're adding sunshades. We're opening up the facades for natural ventilation. The buildings are becoming more porous. And what we're finding is happening is sometimes we're getting narrowband excitations on our forcing spectra. So we can still have a high frequency facade element, but the resultant resonant response, dynamic response, can be high. Excitación de viento de banda estrecha. I might get the animation going on this one. And we've got some narrowband response shown here for wind excitation. And notice starting with this rattling of da, 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 da. Unfortunately, static load laboratory tests of facade assemblies may not prevent this high frequency vibration in the field. We're traditionally testing with static load tests, sandbag tests, for example, and they can miss this phenomena. One of the studies we investigated in a wind tunnel model is a recessed balcony subject to measuring wind pressures inside the balcony walls. It's an enclosed cavity, and the pressures are found to have this narrow band response. There's a connection between the vortex shedding and acoustic radiation within the balcony cavities occurring at the opening for glancing wind directions. And this has been found in other fields previously. Rossiter, back in 1964, observed similarly strong periodic fluctuations in the flow of the bomb bays of B-50-47 aircraft at high Mach numbers, but the fluid mechanics principles were the same. What's basically occurring is we're getting a flow or a vortex separation at the upstream end, flowing down, hitting the downstream end, then the acoustic radiation back at the speed of sound initiates another vortex. And we get the same thing happen again, and we get this loop established, which can actually be defined through this Rossiter frequency function. Now, those same spectra I showed earlier, if they're laid out against velocity in the third axis, you can see these modes appearing, these alignments of the peaks. And what that's demonstrating in fluid mechanics wind engineering talk is a Strull number dependency. What that means is, as the wind speed increases, so does the frequency of this excitation. Explication pour retroalimentation de resonancia de fluidos. Now, another excitation mechanism is Helmholtz resonance. Helmholtz resonance is commonly experienced as a subaudible throbbing. When driving in a car with one window open, you've probably experienced have the window down a little bit at high speed and you feel it. That's a Helmholtz resonance. And it can be modeled with this resonator model, assuming a slug of air mass acting on the stiffness of the enclosed volume with some damping losses through the opening orifice. Now, Vickery and Holmes have derived a formula for the Helmholtz resonance. I won't go through all the variables, but key is Ka and Kb. Ka is the K is the Bock modulus of the air, and Kb is the building volume stiffness. Now, this is important because in real buildings, the stiffness can often be associated with the facade. So you might have, say, balcony doors, and they can flex, and they can actually affect this Kb value in the Helmholtz frequency. Mecanismos de retroalimentación qui competen pour el control. Now, Nadosha describes flow field cases in which mechanisms compete for control. Examples are air column resonance of an organ pipe will alter to the free edge tone to match the resonant frequency of the pipe. It's like the Rossiter dynamic excitation competing with the resonant excitation. This is what happens in woodwind instruments, for example. Now, the same thing can happen in real building flows. At low velocities, say, for example, in a balcony cavity, flows, there is a deviation from Rossiter modes to harmonize with whole building Helmholtz resonance and standing wave modes. Now, this usually occurs in poorly sealed buildings where the whole building volume is exposed and can resonate with low frequency Rossiter excitations. As the wind velocity, keeping in mind these are glancing wind directions, as the wind velocities increase, so does the Rossiter excitation, so it's going to harmonize with smaller building volumes, for example, a balcony cavity. As the wind speed increases further, we start to actually align more with the stiffness of the walls themselves. And we have a transition from, particularly in the serviceability range, from an acoustic loading through to a true wind loading mechanism as we increase in wind speed. Now, we can model this phenomenon using a 2 degree of freedom system mathematical model. So if we have a forcing function, could be the Rossiter excitation, this variable here, acting on the air mass slug within the building cavity. And that's governed by this equation of motion here, where we have a stiffness and a damping. The stiffness is the cavity stiffness. The damping is any energy losses through the opening. And the mass one would be the balcony walls themselves. For example, if it's a door, it's its first modal mass, and it's going to have its own damping and stiffness associated with that. Well, this is quite a complicated model to solve, but in many building applications, it can be simplified, given that for very large flexible doors, the wall frequency can actually asymptote towards the Helmholtz frequency. And in fact, they become one and the same thing in many applications, and this can drop off, so we have a single degree of freedom. It's much more straightforward to solve. Putting in mind too, as we get to higher wind speeds as well, the effect of the slug of air mass is of limited physical mass to actually excite any further. So it tends these acoustic issues tend to be a problem and annoyance in the serviceability range. But then once we move to higher wind speeds, it's basically the elastic response of the mechanical system. And this is the result of a prediction on an example that balcony was showing earlier. We have mid-span deflection versus average recurrence interval, proportional to wind speed. So if you like, your sort of daily, weekly, yearly up to the 1,000-year return period on a log scale. And if you plot it out, you can see some curved deflection response. This is where we have the Rossiter excitation coinciding with the natural frequency of the balcony walls in this particular example. Aeroacustica. Now, wind noise is also a serviceability issue, and it's typically associated with rattling. We all experience a loose facade element, a sliding screen, for example, or rattle in the wind. In itself, that's annoying. But we can also have these edge tones, which is a very similar mechanism to the loading we were just talking about, but rather than produce a load, it's very high frequency in the order of thousands of hertz, creating a noise. Now, I have a sample. You might want to block your ears. It's a high frequency if you want to start playing it. This is a wind tunnel test on a sample, a sheet, perforated sheet. Now you can basically hear the wind tunnel now and then hear this tone coming in. It's about 5 to 6 kilohertz and it's sitting above the background noise. Now, obviously, we don't want that on site. So much better we test in the wind tunnel first before we actually go and assemble the install on site. Now, here's an example of a facade. I'll ask you to start in a moment, but we have a porous sheeting, but a very rigid assembly. No dissipation of energy available. All solid welds and tack screws, so there's no way for the energy to release. If you could start that. And on site, this can be not so loud now, but if it's 90 decibel plus, it can be a real problem. So one of the key things is to avoid small gaps. So small holes in facade, it's rather convenient we've got this. It's about the right scale too. Anything less than 10 mil could create a tone. And if it's on an aluminium sheet, it will resonate and amplify that tone, so it can be quite loud. If we get larger holes, let's just say greater than 20 millimeters, then this is far less likely to occur as we've found in the field. So make sure there's big gaps, if there has to be a gap, like in the screen, and avoid small gaps, not just in screens, but in your assemblies. So where in your facade assemblies, don't have little gaps between your mullions and transoms. Make sure everything is hard flush against each other. And the other piece of advice is include viscous energy dissipation somehow. There might be neoprene washers, but something to absorb the energy. Otherwise, there's no way. You can't just go back to the slab and hope that's going to absorb the noise. It just won't happen. Maybe this is the last one. This is a different phenomenon here. It's just the whole modes of these columns. It's a slightly prettier sound, this one, but it can still be annoying if it's loud. That will pick up in a moment. A little bit of construction noise in the background. Okay, just trying to get to the next slide. Fatiga inducida por el viento. Cargas máximas de viento de diseño auxiliar. So the test we were showing earlier in the wind tunnel on scale models, we look at the facade, say a curtain wall. If you have an element that sits outside the facade, and ancillary, so a sunshade is a good example, it has a pressure on the top and the bottom. It's not a suction pressure against the facade. So to determine the design loads, we need a drag coefficient to combine with the wind load at the location of the installation. So we can test prototypes in the wind tunnel. So we have a screen here. There's even some planting here for a green facade. The client wants to know what the drag coefficient of the vine is. So to give the full drag coefficient information, we test through a range of tilts and yaw angles, and we can define that totally in the wind tunnel. That's all right. Again, if it's a quasi-static load, that works quite well. Cargas de viento de fatiga auxiliar. In real life, we have to also consider fatigue, particularly on elements that are exposed to the wind, such as the sunshade, subject to daily vibration. If we were to say strain gauge a sunshade at its base, we come up with a curve like this, where we have the stress range on the vertical axis and the number of cycles. So it'll see many cycles at a low amplitude of vibration and few cycles at a high amplitude of vibration. But we have to make sure that curve sits below the material capacity, particularly if it's aluminium. We need to be below this level. Rock still has an endurance limit, which is far more amenable to fatigue. But aluminium, we need to be very careful to test these elements. They're not going to fracture after 10 or 15 years in the field. So how do we come up with this curve before we actually have installed it on the site? Well, CPP divided methodology. Actually, my colleague Graham Wood devised this. What it is, it's a combination of 3 wind tunnel scales. So this is Barangaroo International Towers in Sydney. This is a 1 in 400 scale model. And so we first of all do this test to understand the wind environment around the facade. We have a hot wire, we measure wind velocities and wind direction. We get what's called a Weibull distribution. How windy, how often, and from what direction. The second model is an intermediate scale, where we're looking at the interference effects between adjacent fins. And the third test is on the prototype, the full scale, so we can actually calculate the drag coefficient. Now we can combine those 3 scales when we do that analytically post-test, and we're up with a stress range versus cycle count. Now this information can be fed to the facade engineer and fed into their finite element model, and they can then run the check on whether the fatigue life is going to be suitable for that particular installation. Gracias por su atención.